Welcome to Chapter 1. This is our introduction to statistics. We start a discussion with statistical and critical thinking. As you can imagine, in this class we're going to look at a lot of data. What exactly is data though? Data is a collection of observations. Some examples can include measurements or survey responses or assigned gender. Statistics, on the other hand, is the science of planning studies and experiments, obtaining data, and then organizing, summarizing, presenting, and analyzing, and most importantly, interpreting those data, then drawing conclusions based on them. Let's think of some ways that we could obtain data. Data can be obtained through surveys, polls, physically taking measurements, observations, as well as many other ways. Let's think about how we could summarize data. Sometimes when we summarize data, we simply give the mean and the standard deviation. Other times, we might summarize the data in a chart or a graph. We might draw a diagram or create a histogram. There are lots of different ways to summarize data. And summarizing data is important. Just looking at a giant list of data values doesn't give us very much information. But summarizing the data in a useful way can bring some important characteristics to light. Take a moment to think about how you've seen data presented. Think about graphics, flyers, commercials you've seen. Data is often presented all around us. Now let's talk about the difference between a population and a sample. A population is a complete collection of all individuals that are to be studied. So for example, if we're conducting a survey on which toy is the most popular among 5-year-olds at Christmas time, who would the population be? The population would be the complete collection of all individuals that are being studied in this case. So the population would be all 5-year-olds. And by all 5-year-olds, we mean all 5-year-olds, anywhere. For another example, if we give an antibiotic to rats with an E. coli infection as part of an experiment that we are conducting, who would the population be? Again, we want the complete collection of all individuals to be studied. So in this case, the population is all rats with an E. coli infection. And again, by all rats, we mean all rats that have an E. coli infection anywhere. If we're looking at a population and we collect data from everyone in the population, we are doing what's called a census. A census is a collection of data from every member of the population. Think about if this is always going to be possible. If I'm conducting a study about our class and the population is simply my students, it wouldn't be too hard for me to conduct a census. But if the population is all adults over 20 years old, how on earth would I ask them all? Think about the cost of a census. Think about availability of all of the subjects. Think about the time commitment that would be involved. And even if you do find all of the subjects, they may not all be willing to participate. So with a census not always being a possibility, we instead can look at a sample. A sample is a sub-collection of members from a selected population. For example, let's say that 50 cats from a shelter are weighed and the average weight was found to be 9.5 pounds. What would be the sample in that case? I'm assuming that there's more than 50 cats in that shelter, and all of the cats in the shelter would be the population, but the 50 cats that were chosen and actually weighed are the sample. When we're drawing a sample from a population, it's really important that the data is chosen as randomly as possible. Random samples are often more representative of a population, and they help us avoid bias. One type of sample is a voluntary response sample. A voluntary response sample is a sample in which people choose to participate. Imagine walking out of a store and having somebody stand outside the door and asking you a question. You get to choose to answer the question or decline. Think about if a voluntary response sample is a good way to decide who participates in a sample. Are you more likely to participate in a survey if it's an issue that you're passionate about? Probably. There's an automatic bias built into voluntary response samples. Those that volunteer or respond are likely much different from those that don't. So this is not a random sample at all. Now let's turn our attention to what's called a statistical analysis. When we're doing a statistical analysis or analyzing a statistical analysis done by someone else, we need to keep these 5 things in mind: context, source, sampling method, conclusions, and practical implications. Let's look at each of these items. First is context. That's where we ask the question, what do the data represent? And what is the goal of the study? For example, look at this table of values. Are these data sets matched in a meaningful way? Not really. What does X represent? What does Y represent? What relationship are they trying to show here? I don't see enough information to be able to talk about the context. When thinking about the source, we ask the question, are the data from a source with a special interest so that there's pressure to obtain results that are favorable to the source? Let's look at this example. A survey is given to people at a grocery store in town asking which grocery store is the best. Alpha Beta Grocery Store won. Congratulations! But upon investigation, it was found that Alpha Beta was the one that organized and paid for the survey. So now what do you think of those results? If Alpha Beta organized and paid for the survey, it's pretty likely that they asked customers that were already at their store and likely to shop there and think that that grocery store is the best. So there's definitely a built-in bias. What we're seeing here is an important point. Free response studies tend to be biased. This also emphasizes the importance of a random sample. Which brings us to our next point, the sampling method. Were the data collected in a way that is unbiased, or were the data collected in a way that is biased? To wrap our heads around this, let's look at these two examples. First, suppose that a college wants to conduct a study to find out the average BMI or body mass index of students on their campus. They send out an email to all of the students asking them to come into the health center and get weighed. Do you think this is a good sampling method? Probably not. Students that are not happy with their weight are a whole lot less likely to come in and be weighed. This sample is not going to be representative of their campus, and it's not a random sample. Take a moment to think about how this study could be improved. How could the college conduct this study in a better way? For another example, suppose a college class wants to conduct a poll asking people what their favorite fast food restaurant is. Students from the class take turns standing outside of KFC across the street and asking people coming in and out of the restaurant, what's your favorite fast food restaurant? Do you think that's a good sampling method? Absolutely not. If they're standing outside of KFC, then they're only asking a certain type of person, or a person that's likely to choose KFC or similar restaurants. Take a moment and think about how this survey could be improved. Next, we need to consider the conclusions of the study. We're going to read all statements in the conclusion and take note of any statements that don't seem to be justified by the statistical analysis. Here's an example. Bobby notices that as time passes, the ice cube that he's observing is appearing to melt. So Bobby concludes that time passing is causing the ice cube to melt. Is Bobby correct? Is time what's causing the ice cube to melt? No. Is there a correlation there? Absolutely. As time passes, if an ice cube's sitting on the counter, of course it's going to melt. And as time increases, the amount of water on the counter will increase. So there is a correlation. But there's a lurking variable there that Bobby's not considering. It's temperature, right? If it was really time that was causing the ice cube to melt, then all of the ice cubes that are currently in my freezer would be melting as time passes. So that's not the cause. This brings up a really important point. Correlation, or a relationship between two variables, does not imply causation. Just because there's a strong correlation between two things does not mean that one of them is causing the other. Finally, we'll look at practical implications. After you look at all the conclusions or state your own conclusions, we need to think about the practical implications. That's the difference between what the numbers say and what common sense says. For example, if the results of an experiment suggest an increase in blood pressure when there was an increase in caffeinated beverages consumed, then the practical implication would be that caffeine may result in harmful health effects. And speaking of practical implications, let's talk about the difference between being statistically significant and practically significant. What does it mean for something to be statistically significant? This happens when a result occurs that is very unlikely to happen by chance. We typically use a threshold of 5%. We would say that a result is statistically significant if the likelihood of that event happening by chance is less than or equal to 5%. In contrast, practically significant is something different. It is possible that some treatment or finding is effective, but common sense might suggest that the treatment or finding does not make enough of a difference to justify its use. Let's look at an example to see the difference between these two. There's a diet plan that claims if a person follows it for a year, they will lose weight. 100 people followed that diet plan for a year, and every single person lost weight over that year. The average amount of weight loss was 0.78 pounds. First, let's talk about if this is statistically significant. It actually is. If you took 100 people and just followed them for a year, the likelihood of every single person losing weight in the group is very, very unlikely to happen by chance. So this result is statistically significant. But think about this through the lens of common sense. The average amount of weight loss was 0.78 pounds. Is it practical to sign up for this plan for an entire year just to lose less than a pound? Probably not. So this event is statistically significant, but it's not practically significant. That concludes this lecture video for Chapter 1, where we talked about statistical and critical thinking.